Hi, I'm Brian,
And I'm Mac.
and our presentation is on the physics behind the trebuchet.
Our experiment is going to be to vary the mass of the counterweight on the trebuchet to see the effect on the distance of the shot is thrown. So the calculated amount of kinetic energy for this experiment, we know the potential energy is the same as the kinetic energy, which equals mgh. Since potential energy in this case is 32 kilograms, which is the weight of the counterweight, times 9.81, which is the acceleration of gravity, times 0.66 meters, the distance of the drop. And that all equals the kinetic energy. Therefore, we know that in this case, potential energy is 207.1872 joules, which is the same as the kinetic energy. So with a 32 kilogram weight under ideal frictionless conditions, we should be able to produce 207.1872 joules of kinetic energy. For our second experiment, the weight is reduced to 16 kilograms, and our calculations would be the same, resulting in 103.5936 joules of kinetic energy. To calculate the force of the throw itself, we know that force equals mass times acceleration, therefore force equals 32 kilograms times 9.81 meters per second, which gives us a force of 313.92 newtons.
Where's the kaboom? There was supposed to be an earth-shattering kaboom.
We collected the data and performed calculations on a series of test shots. We did 10 shots with 32 kilograms and 10 shots with 16 kilograms as the counterweight, calculated our velocities and our kinetic energy levels per shot. We then created a chart plotting the distances for each shot on a side-by-side comparison so we could see the differences. All right, so our ideal results using a 32 kilogram counterweight, we can calculate what distance we should get from a trebuchet if everything is working well. Now the distance should equal 2 times mass 1, which is the mass of the counterweight, divided by mass 2, the mass of the object thrown, times the height of the drop of the counterweight. In this case, so that would be 2 times 32 kilograms divided by 0.193 kilograms times 0.66 meters. That would be 2 times 165.803 times 0.66 meters, which works out to 331.606 times 0.66 meters. So our distance for the ideal shot under perfect conditions should be 218.86 meters with a 32 kilogram counterweight. Let's see what happens.
Okay, you're good. Nice. Okay, so the actual results of our 32 kilogram counterweight throwing the softball actually ended up being, our average results ended up being 73.508 meters. Not nearly as far as we were ideally hoping for, but there are a lot of things that come into play with that. There's friction of the trebuchet between the different parts. There's the weight of the softball compared to its size, which actually the wind resistance acts a lot more drastically upon it. Also, our trebuchet was a little wobbly. We tried to stabilize it as the best we can, but I mean, we did what we could, and it still was a little wobbly, so there was loss on that. Also, the softball, when it spins in the air, is actually losing energy from the spinning. So there's a lot of factors that played into the drastic difference in the distance that we got and the distance we should have gotten. Okay, so for the ideal results for the 16 kilogram counterweight, let's just start again with the basic formula. It's going to be distance equals 2 times mass 1 divided by mass 2 times h. Now, mass 1 is the mass of the counterweight, being 16 kilograms. Mass 2 is the mass of the softball, being 0.193 kilograms. And the height, h, is the height of the counterweight and the distance it drops. So that's the distance it ended up dropping was 0.66 meters. Break it down, 2 times 82.902 times 0.66 meters ends up being 165.803 times 0.66 meters, and we get the final result of the distance being 109.430 meters. You're good. And what?
Okay, so our actual observed results for the 16 kilogram counterweight shots ended up being an average distance of 37.22 meters, which is considerably shorter than we had planned under our ideal circumstances. And again, the reason for that would be the density of the softball. A softball is a fairly large surface area and a fairly low weight, low mass, which of course means that it's not really going to travel as far. Had we used, say, a hard ball, we would have got a much greater distance out of our launch.
Okay, so for our percentage of error, on a 32 kilogram counterweight, we had an average distance of 73.508 meters. On our calculated, we actually had 218.86 meters. Now the percentage of error ended up being 66.4%. Pretty dang big. Let's move on. The 16 kilogram counterweight, our average distance that we got was 37.22 meters. Our calculated distance was 109.43 meters, resulting in a 65.9% percentage of error. Now, the percentage of errors are actually very close. So it's not necessarily that we did something super wrong, it's all the reasons behind it. It's the size of the softball compared to the weight of the softball. The ideal release angle at 45 degrees, which is what you're supposed to obtain, we might not have gotten that. We adjusted, but I mean, when you're hammering a nail back and forth, there's only so much adjusting that you can do. Also, the wind that day, adding to normal wind resistance, you have wherever the wind was going that day. Also, you have the friction in the actual mechanism of the arm. On top of that, you have our trebuchet wobbled, so there's a lot of energy lost. Another factor that has a small contribution is the spinning of the ball actually releases energy. So you lose some energy in that also.